Dear students, in this clip let us learn how to do construction of space diagram. First of all, what is space diagram? Space diagram is also popularly known as configuration diagram. A configuration diagram is a line diagram. In fact, it is a skeleton that represents the given mechanism. In fact, for any velocity or acceleration analysis, the first step would be construction of configuration diagram. The meaning of configuration diagram will be best understood with this illustration. So what we see here is an IC. This machine IC engine has slider crank mechanism in it. So the slider crank mechanism is shown separately. The involved slider crank mechanism, if it is drawn by a line diagram, a skeleton diagram, that obtained diagram is known as configuration diagram or space diagram, which is shown. Let us take one example, a numerical example, to illustrate the construction of configuration diagram. The numerical problem goes like this. One link is fixed, which is PS here, then other lengths are known, and also one angle QPS 6 degree is given. The given data are listed one by one, as always we do in all numerical problems. So our aim is to learn how to construct the first step of any analysis known as configuration diagram. Since it is a graphical method, first we need to keep all the required items ready with us, like pencil, scale, protractor and compass. Right. So for the space diagram, first we have to take a suitable scale. Here, for example, 200 mm PS is the maximum length, which is given as 200 mm. So what we take is 1 centimeter equal 20 mm. We take the scale and we draw the PS. Then to get the Q, we know the length PQ and also the angle 60 degree. Using the angle 60 degree and the length, we get the point Q. So the next point would be R. To get that R, QR is given 175 mm. Take an arc, by taking Q as a center, QR as a radius. Similarly, make one more arc, taking S as a center and SR 112.5 mm as a radius. Draw that. The intersection point will be the required point R. So join those 4 points, we get the required PQRS, which is nothing but the configuration diagram. So after drawing that, we have to show all the given dimensions in the diagram. This is how we need to draw. The most important thing is selecting the most suitable scale. Thank you. Students, in this video session, let us learn how to construct a velocity diagram by taking a numerical illustration of a 4-bar chain. As you are aware, there are 4 steps involved in velocity analysis of any mechanism. The step number 1 would be construction of configuration diagram, also known as space diagram, which we have already detailed in our earlier video. The second step, we have to calculate velocity of any one link. In order to start with the velocity diagram, at least for one link we need magnitude and direction. Since the angular velocity and length of the input link is known, so we could find velocity of the input link by using the equation V equal to R omega. By using the known magnitude and directions, we can complete the velocity diagram, which we will illustrate very soon. Once the required velocity diagram is completed, just by measuring the lengths, we can obtain the required velocity of links. Let us illustrate the above 4 steps by taking a numerical problem. Here a 4-bar mechanism problem has been chosen. Here the PQRS is a 4-bar mechanism. The fixed length is PS and the lengths of 4 links are given along with angle QPS, which is 60 degree. If you could remember the same numerical problem we illustrated for the construction of configuration diagram. Once the given data are listed out, then our aim of this problem is to determine velocity of various links as well as angular velocity of links Q, R and RS. Now let us go to the solution. Right, the step number 1 would be construction of configuration diagram. Since we have already done in detail, we are taking the answer as directly. So now let us see the step number 2, where calculation of velocity of the input link. V equal to R omega. By using that equation we get the answer 0.625. To start with, anywhere you put a dot, since the points P and S are fixed, it will have zero velocity. So it starts with a dash. You can put arbitrarily anywhere. Now we are going for the next link. No, I want to find point Q. Since we know the PQ 0.625, I am taking a suitable scale. So here I use the scale 1 centimeter equal to 0.1 meter per second, by using which I am drawing the line. More importantly, that line is perpendicular to PQ. Then we do not know the magnitude of velocity of QR as well as length RS, but we know the direction. So we need to draw perpendicular to QR and RS as shown. When you draw the perpendiculars, it intersects at one point R. Join them, we get the required velocity diagram. So there you are. We got the required velocity diagram PQRS. So now just by measuring the three sides of them, we will get the required answers VQ, VRQ, VRS. Finally, once the velocity diagram has been completed, now we could find all the required data. So just by measuring the vector QR, we will get velocity of RQ, which is 0.35 meter per second. Similarly, measuring the velocity RS, then multiply by the appropriate scale, we will get the answer VRS, 0.44 meter per second. But the required answers are angular velocity. So V equal to R omega, therefore omega equal to V by R. So omega QR is equal to V QR divided by QR. Since both are known, we can get the answer 2 radians per second. Similarly, angular velocity of the RS can be determined as 3.91 radians per second. That's it. Dear students, in this video let us learn how to draw acceleration diagram by taking a numerical illustration. As we know, there are 6 steps involved in acceleration analysis of any mechanism. The first step being construction of configuration diagram. Step number 2, calculation of velocity of the input link. Step number 3, using the known direction and magnitude, we have to construct the velocity diagram. Then step number 4, once velocity diagram is done, we can calculate the velocity of various links by just measuring the lengths. In step number 5, we are going to construct acceleration diagram by using the known magnitudes and directions. Finally, once acceleration diagram is done and dusted, we are going to measure the various sides of it in order to find acceleration of various links. We are going to illustrate the step number 5 and 6 by taking a numerical problem. So what we need to find is angular velocity omega of links QR and RS, as well as angular acceleration alpha of links QR and RS. As we are aware, already we have determined angular velocity of the links QR and RS in our previous video. So now our main focus will be on determination of acceleration of various links. Let us see the construction procedure now. As discussed already, the problem can be attacked through 6 steps mentioned. So the first 4 steps have been already covered in our previous 2 videos. So it has been summarized here. Now we will move on to construction of acceleration diagram. In order to draw the acceleration diagram, we need to know the various components of acceleration. There are two components, namely radial component and tangential component. So radial component will be parallel to the link, whereas tangential component will be perpendicular to that particular link. So since we have four links, we have to find for each link its radial and tangential component. So it is better to make a table and find all the known and unknown values. So the first link is PS. Since it is fixed, both radial and tangent component is 0, as you could see from the table. The second link PQ, since velocity and radius is known, the radial component AR equal to V square by R, we can find 6.25 meter per second square is the radial component, and also the direction is always parallel to the link QP. Since in the problem it is given that omega, angular velocity of the PQ, is constant, therefore alpha is 0. Since angular velocity omega is constant, therefore tangential component will be 0. The third component, we have QR. We can find AR the same manner. We get 0.7 meter per second square, but we do not know yet the tangential component of it. Similarly, for link RS, the radial component value will be 1.72 meter per second square, and the direction is parallel to RS, whereas we do not know the tangential component of RS, but we know its component will be definitely perpendicular to the link RS. Once having known known and unknown values of both the components, radial and tangential components, now we are ready to construct the acceleration diagram. Let us continue from step number 5. Already we have completed space diagram and velocity diagram. Now let us draw the acceleration diagram. Let us give namings as P dash and Q dash. So you take arbitrarily anywhere a starting point. Since P and S are fixed point, their acceleration, both radial and tangential components, are 0. Therefore, the acceleration P dash S dash will be just a dot. Now we can try to get Q. So for acceleration of PQ, we have two components. One is radial component. From the table, since we know that 6.25 meter per second square, we can take the shootable scale. Here we take 1 centimeter equal to 1 meter per second square, scale. Therefore, for 6.25 mm, we are drawing a line which is parallel to the PQ that represents the radial component. Tangential component for PQ is 0. Therefore, the total acceleration itself the same. Now we will try to get the point R. First we will try to draw QR. For QR, we know the radial component. Since the magnitude is known, direction will be parallel to QR, so we can draw the vector. So this vector which we draw now represents radial component of AQR, whereas the tangential component is unknown. So therefore, what we can do is we can draw perpendicular line for some arbitrary length. We know that tangential component will be always perpendicular to its radial component. So simply draw a perpendicular line. That's it. We do not know the exact magnitude yet. Now let us get the point R from SR. Since we know the radial component of SR from the table, we know the magnitude. Direction, of course, is parallel to SR. Using the known magnitude and direction, now from point S, we can draw SY, which is parallel to SR. So this line what is drawn represents radial component of acceleration of RS. Now we need tangential component. As you could see from the table, tangential component is unknown as of now, but we know it should be perpendicular
to the radial component. So what we could do is, from that point to y, we can draw a perpendicular to s dash y line. Of course, length is not known, so simply I extend. Where these two lines extend must be the most important point known as R. So we got the point R dash. Now our requirement is to determine acceleration of QR, therefore join Q dash and R dash line. Similarly, to determine acceleration of the link SR, join S dash and R dash points. So the red line indicates the required acceleration, total acceleration, whereas the blue ones represents the components of it. Once we complete the acceleration diagram, we can measure those sides of it. We will get the required acceleration, various acceleration of links. Here, after measuring, we need to multiply by the scale chosen. Then only the exact value will be obtained. But in the given data, they have not asked the total acceleration, they have also asked the angular acceleration. As we know, angular acceleration, the formula being alpha equal to tangential acceleration component divided by length of that link. So for example, I want to find alpha QR, AT RQ divided by QR, we get the answer. So how can I find AT QR, which is highlighted in the diagram? So just to measure them, divide by the length of it, we get the required answer. So hope you have understood how to construct the acceleration diagram and its calculation. Thank you.